This is the third segment by Dr. Tausman, week 2, talking about central tendency and variability. So now we're going to move into Roman numeral 2, problem number 2. Take a look at the data sets 5 and 6 here for just a minute. Data set 5, 2, 3, and 4. Data set 6, 2, 2, 2, 3, 3, 3, 4, 4, 4. Now if I were to ask you in terms of the dispersion for these two data sets or the variability, do these two data sets look similar or different in terms of their dispersion, just in the basis of eyeballing it, just looking at the numbers? Well, most people would say that really in terms of the dispersion, data set 5 should actually be somewhat comparable to data set number 6, because the numbers are kind of the same spread between the lower and the upper one, 2, 3s, and 4s, just the case that data set 6 has 3 of each of these. So the question that we would have then is, okay, if their dispersion is just about the same, why don't we actually get our one good measure of dispersion that we use most often in psychology and statistics, which is what? The sum of the square deviations. And you'll hear me abbreviate that, sums of squares. So if that is indeed the case, if you take data set 5, any 3 consecutive numbers, 2, 3, and 4, the sums of squares is always going to be what? 2. That's true for 2, 3, and 4, 1, 2, and 3, 100, 101, 102, because the dispersion is the spread in the scores. So the sums of squares for data set 5 is going to be 2. And how about for data set 6? Take a minute or so and see if you can compute that. Hopefully you end up getting the value of 6 for the sums of squares, because it's 2 minus 3 squared, 2 minus 3 squared again, 2 minus 3 squared a third time. The 3's all are zeros, and then 4's, it's 1's again, so you get a sums of squares of 6 there. Now the question I have for you, is that fair? Is that unbiased? Hopefully you would answer no for that, because data set 6 and data set 5 really look the same for their dispersion. So the fact that data set 6 has the sums of squares of 6 and data set 5 has the sums of squares of 2 is really not so good. It means that the sums of squares can be a little biased sometimes. It can be biased when you have different populations. So in this case, data set 5 has only 3 scores in the population. Data set 6 has 9 scores. So if you have a lot of numbers in a data set, the sums of squares just tend to come out usually higher. So this is kind of a biased estimate of dispersion when you have different size populations or samples. So this is a bit of a problem. The question I have for you is there anything we can do to fix this? And most of the time people answer yes for this. The way we could fix this is if we get the sums of squares first, and then if we actually divide it by the total number of scores that are in the data set. So why don't we try this? Get the sums of squares for data set 5. What did we say that was? It was 2. Now divide that by how many total scores are in there, which is what? 3. So the sums of squares for data set 5 is 2, but this new value, and this new value is called D, variance, the new value, variance, would actually be what? 0.67. So that's for data set 5. Can you actually do the same thing for data set 6? What are the sums of squares? It's 6 divided by how many total scores there? 9. So 6 divided by 9 is what? 0.67 again, 2/3. So variance is actually a new useful measure of dispersion, because variance also stands for the average sums of squares. It's like the mean sums of squares, because you divide the sums of squares by the n, don't worry about the df at this point, by the n in that group. So variance is most frequently used, and you'll see it on page 113. Variance is the sums of squares over n, which is a good, accurate measure, especially when we have different sizes of the sample or different sizes of the population. So we like to use variance as a real accurate estimator. It's also called the mean square. the mean sums of squares, or the mean square. Why is it a mean square? Because it's really got a nasty edge to it, and it can curse people out. No, that's not the reason it's a mean square. So we often use variance as an estimate of that. The other one, if you follow the formula down a little bit more, besides using the variance many times on page 113, the last one that is also considered an accurate indicator is the standard deviation, where you take the square root of the variance. I don't have my calculator right here, but you would take the square root of 2/3 of 0.67. And in this case, you notice that the variance and the standard D for both of these groups are the same, which is good, because we said when we were eyeballing things that data set 5 should have a similar measure of dispersion as data set number 6. So we use the sums of squares as one measure of dispersion, but it's only good to use the sums of squares when the populations they're coming from are about the same in terms of the size. If they're not, it's best to use the variance, which is the sums of squares divided by the n, or the standard deviation, which is the square root of that. So let's see what we've got under that. Pretend that you are still dealing with the same numbers you had in problem 1. Would anything be different if I told you that the 3 scores from JMU came from a class of 20 students, and that the 3 scores from Mary Baldwin came from a class of 20 students? Got to pause the tape here. This will be the last lecture. Thanks. Bye-bye.